Welcome to this video for the Higher Physics course, in the Dynamics universe, looking at explosions, part of the momentum topic. So what are we looking at just now? We're looking at how to carry out calculations for explosions in just the one dimension. So in an explosion, the momentum before is often zero, because something that's exploding may be stationary, and then when it explodes, pieces go in all different directions, but the total momentum of all the objects in different directions will still be zero. So the momentum is conserved. Remember, the law of conservation of momentum says the total momentum before is equal to the total momentum after, unless acted upon by external forces. So we have a bomb splitting in different directions, or if you were standing with a big heavy ball and you pushed the ball off and you were standing on a skateboard, then the ball would move to the right as shown in this picture, and the skateboard and person would move backwards to the left. We see this in the recoil of guns, where we're firing a bullet or a missile or a cannonball, that type of object, in one particular direction, which has a relatively low mass but a high velocity, and that means that the cannon moves backwards in the opposite direction, or the artillery gun. So explosions are the same way as collisions. They're treated in the same way. The total momentum is conserved unless there's an external force. So in the case of firing a bullet from the gun, the total momentum before is zero, and then we've got the bullet moving forwards with a particular velocity and the gun moving backwards with a particular velocity. Okay, so one will have a positive momentum in one direction, and because velocity is a vector, the velocity in the other direction will be negative. So when we add up those two, the positive one forwards and the negative one backwards, we get a total of zero. Okay, there's a couple of clips here that I'll put the links in with the work that show recoil of guns. This is why when people are firing guns, they tend to lean into the gun to make sure that it's not going to come backwards and hit them. So in all explosions, the momentum is conserved. And so if we're looking at the object beforehand, it's often stationary. And we look at it afterwards, we've got one object moving one way with a particular velocity and the other object moving the other way with another velocity. And remember, one of those velocities will be positive and one of those velocities will be negative. In our cases, we're just looking at ones that are going in just the one direction here, so just the one plane. So in reality, in an explosion, bits go in all different planes, but all the ones we're looking at are just going right and left or up and down, rather than in a multiple sense of directions, to simplify the model. Okay, so the total momentum before is equal to the total momentum afterwards. We've got one term before because we've got one thing there, and we've got two terms afterwards because we've got two pieces that it's splitting up into. And a reminder that one of the velocities will be negative. Here we've made that V1. Okay, so let's look at a particular example here. We've got two trolleys that are both at rest, they're touching each other, and they fly apart when we release a plunger. The dynamics trolleys in the classroom have a thing that you can push down and the spring-loaded pole pushes against the other trolley. Okay, so one has a mass of 2 kilograms and moves at 4 meters per second. The other one moves in the opposite direction at 5 meters per second. And we're asked to calculate the mass of this second trolley. Now we can see that it's going to be different because it's moving off at a different speed to the other one. If the objects have the same mass, they will move at the same speed. So we can start with our diagram. There are our two trolleys together in the before condition. There's our trolleys afterwards, and we can put on our information. Okay, we've got -4 because one's going in one direction, and we've got +5 because the other one's going in the other direction. Okay, so then we can substitute in. So our total momentum before is 0 because it's stationary, And then we've got 2 times minus 4 plus m times 5. So 5m is equal to 8, and therefore the mass is 1.6 kilograms. Okay, let's have a look at a second example here. So we've got a missile that is launched vertically, it reaches its maximum height and then explodes into 2 individual warheads. At its maximum height, its vertical velocity would be 0 at that point. And it explodes into 2 that move off. One moves off horizontally, and we're asked to work out the velocity of the other one. Okay, so it's splitting into 2 equal parts. So we're showing that information in our picture at the bottom. Remember, our pictures don't have to represent exactly what it looks like. We've got boxes to represent the situation here. Okay, so we've got our before, we've got our after conditions here. The total momentum before is equal to the total momentum afterwards. And our mass times velocity before will be 0 because it's stationary, because it's at its maximum height and it's not moving horizontally, and therefore we've got 1500 times our velocity plus 1500 times the 2.5 kilometers per second, which we've changed to meters per second. So we substitute in our numbers, we can rearrange, and we end up with the fact that the speed in the other direction, because it has an identical mass, half the mass, will be the same as the speed to the right. So the speed at 90 degrees is 2.5 kilometers per second. The speed at 270 degrees in the opposite direction is also 2.5 kilometers per second. Okay, so what we've shown here is we've shown how to carry out calculations for explosions using the laws of conservation of momentum.